Today's class, we're going to move on to a topic that's called induction. And the topic of induction is really the beginning of our work on joining together electricity and magnetism, two topics we've discussed so far. I said electricity and magnetism are really married together. They're one kind of electromagnetic force, so we're going to begin our work on that. Ultimately, we'll discover that light is an electromagnetic phenomenon, and so that's our ultimate goal here. Today's class, I'm going to introduce the discovery that changing magnetic fields, so it's time-varying magnetic fields, actually produce electrical currents, electrical potentials. So that's the phenomena of induction. To quantify induction, to be precise about induction, I'm going to introduce the concept, the notion of magnetic flux. It's like electric flux, but it's for magnetic fields rather than for electric fields. So we'll explore magnetic flux. And then to further quantify induction, I'm going to introduce the law called Faraday's Law, the law of nature called Faraday's Law, that describes induction, that describes the creation of induced currents, induced EMFs by changing magnetic fields. So that's the plan. Okay. Well, she hasn't been to class for a while, but today is is the beginnings of a really important step for us. As I say, up to now we've treated electricity and we've treated magnetism as if they're separate worlds. Electric forces and magnetic forces are just separate forces. But there was an obvious clue. I kind of kept it secret, but you might have spotted it, that electricity and magnetism are not separate worlds. Ultimately, electric forces are due to a dimension of nature that we call charge, electric charge, and ultimately magnetic forces, they arise also from that dimension of nature that we call electric charge. So at their core, at their heart, electricity and magnetism are both due to electrical charge, both due to this new dimension of nature we discovered in Physics 2.13, this electric charge. We're going to, as we study induction, we'll be exploring the connections between electricity and magnetism. And as I say, it's going to lead us to some discoveries about some secrets that light is actually holding. Okay. This is a sort of famous picture. You see it in textbooks. It's a famous example of induction. So in this picture, there are hundreds of fluorescent lamps here. You know, here's one, and then there's just rows and rows and rows, columns and columns and columns of lamps. And you can see they're all lit. But actually, none of them are electrically connected to anything. They're just stood upright in some farmer's field, and they're just lit without being wired up in some circuit. So how is that possible? That's possible because of induction. That's possible because of induction because, you might notice it here, above the fluorescent lamps are power lines. So upstairs here, these dark lines, you see a handful of them, are power lines. So electrical power is streaming, electrical current is streaming through those lines. That electrical current, that electrical power, is what we call AC power, AC current. It's alternating current. It's time-varying current. And that time-varying current produces time-varying magnetic fields, changing magnetic fields. And it's the changing magnetic fields that are lighting the lamps, that are lighting the fluorescent lamps. And that's how they're lit. is through the phenomena, through the effect of induction. Okay, so induction was just this two scientists that were really important in the discovery and the application of induction. One is English scientist who was Michael Faraday. Here he is. This slipped off his brain for some reason. I put it up here, but it fell off. And then there's a second very famous scientist, an American scientist called Henry, he really worked on applications of induction. So Michael Faraday, we've met before. Henry, we have not met before. Michael Faraday, if you remember the story, he's a scientist that really had no formal education. But he had a lot of ideas. He was a great experimenter and uncovered a lot of things. One of the ideas that he had was that of the field, the notion of the field, the concept of the field as a carrier, a mediator of, say, electric forces or magnetic forces. So that was a fantastic and breakthrough idea. The other famous experiments he did were related to induction. He was really the person that discovered induction. And as it says on this slide, induction was really the breakthrough that has led to our kind of modern technological lifestyles. All our modern technological devices are based on induction. So without Michael Faraday, we would have no iPhones or iPads or whatevers. We'd be sort of living in some sort of technological wasteland with oil lamps and things like that. Okay. So this is Joseph Henry. He just missed being credited with the discovery of induction. So Faraday just fractionally beat him to the discovery or publication of induction. However, it was really Henry that developed a lot of the applications of inductance, from things like electrical generators to things like electrical motors that have led to our modern technological lifestyles. So he really developed the idea of induction and applications of induction. Okay, so let's get on with induction. So Faraday, for who knows what reason, was looking for links between electricity and magnetism. He was curious about links between electricity and magnetism. And on this slide and the next couple of slides, we'll see one of his experiments to look for links between electricity and magnetism. So if you look on this slide, over here on the left, we've got a magnet. So here's just a regular bar magnet. North pole, South pole, magnetic field lines emerging from the North Pole. Those field lines return to the South Pole. So that's a magnetic device. Over here, we've got an electrical circuit. We've got a loop of wire. It could be one turn of wire like this sketch here. It could be many turns of wire in practice. And it's connected to a multimeter that could, say, measure the current in the wire or could measure the voltage in the wire. This is an electrical device. So this is an experiment that naively, right, is a bit stupid, because this is an experiment in which we've got magnetism downstairs here on the bottom right, and we've got an electrical device over here on the top left. And it's looking for something that was not known to exist, a connection between electricity and magnetism. If you put the magnet next to the loop of wire, we just put it on the desk next to the loop of wire, you see nothing. So there's no current in the loop of wire. There's no voltage across the ends of the loop of wire. You see absolutely nothing with this magnet just sitting there on the desk next to the loop of wire. However, what Faraday discovered was an effect when he approached the loop of wire with the magnet, and when he removed the loop of wire from the magnet. So this slide and the next slide shows you the effect. So when Faraday brought up the magnet towards the loop of wire, at that moment, so I'm just going to lift the magnet over to the loop of wire, he saw a current in the loop of wire. He saw a voltage in the loop of wire. It goes away as soon as you put the magnet in the loop of wire or nearby the loop of wire, but it's just that moment you bring the magnet up to the loop of wire. He also noticed when he took the magnet away from the loop of wire. At that moment he removed the magnet from the loop of wire. Again, he saw in his multimeter there was an induced current flowing in the loop of wire. There was an induced EMF, an induced voltage between the terminals of the loop of wire. So again, this is a momentary phenomenon as he pulls the magnet away from the loop of wire connected to the multimeter. And so this moment, I don't know whether it was over a few days or whatever in his little lab in his basement, but this was the moment that electricity and magnetism started to get joined together, started to get what we call unified. Let's, I think, repeat his experiments. I want to show you them. Yeah. So I got a few demonstrations of them, and in all of them, there's going to be a common feature. I'm going to change one way or another way a magnetic field. So there's a few ways I can change a magnetic field. I can do what Faraday just did, which is move a magnet here or there. Or I could use an electromagnet, and I could switch the electromagnet on and off. That would be another way of changing a magnetic field. So we're going to look at different ways of changing magnetic fields, and by looking at different ways of changing the magnetic fields, we'll see the effect of induction. Okay, so you've got to imagine that I'm Michael Faraday. That's a terrible thought, because he's dead. But anyway. So what have I got here? Let me explain what I'm doing. I've got a loop of wire. Okay, this is many loops of wire, because you actually want many loops of wire to more easily see the effect. It's connected to Michael Faraday's original multimeter here. No, it's not connected to it because I've messed up the connection. What have I done? Should be connected to it now, I hope. So it's a loop of wire, many turns of wires connected to Faraday's multimeter. And if you see on the multimeter right now, the needle's at 0. And what I'm going to do, I've got a bar magnet, so exactly Faraday's experiment, and I'm just going to shove the bar magnet into the loop of wire. And so let's do that. And you see I hope you see it. Might be hard to see at the back. There's a deflection of the needle. It went over there towards the right-hand side of the room. Now I'm going to take the needle out, the bar magnet out. And you see it deflect in the opposite direction. It's just at that moment, instant, that I am moving the magnet. I put the north pole into the loop of wire, and the needle went towards the right when I put it in, and it went towards the left when I pulled it out. If I did the reverse, now I'm going to put the south pole in. So I push the south pole in, the needle flies over towards the left-hand side this time. When I pull the south pole out, it flies over towards the right-hand side. Anyway, that was Michael Faraday's famous experiment. It's not hard to set up, but it was the beginning of sort of this earth-shattering change in how we think about electricity and magnetism, that we think about them as connected with one another. Let's look at another example. So what I've got here is 2 coils of wire. So this is like, remember we call chains of coils of wire. We call them solenoids. So these are two solenoids. There's a smaller diameter one here, and then there's a larger diameter one here, such that I can put the smaller one inside the larger one. Now, importantly, there's no electrical connection between the larger diameter coil and the smaller diameter coil. So they're not electrically connected by some electrical circuit. The smaller diameter coil is connected up to this power supply via this switch. The switch is open right now, but I can turn it on. So I could energize this solenoid and create a magnetic field with this solenoid. The larger coil is just connected with these two wires, the red one and the black one, to, again, one of Faraday's multimeters. And right now, it's reading 0. So what I'm going to do, again, you've got to watch the needle. I'm going to switch on the solenoid, the small solenoid that's inside the large solenoid. Remember, these two solenoids are not wired together. They're not connected together. And let's just watch when I close this switch here. Momentarily, again, the needle this time flipped towards the left, moved towards the left. There was a brief momentary current. There was a brief momentary voltage. I'm still holding the switch shut. So right now there is a magnetic field created by the inner solenoid that's bathing the outer solenoid, but nothing is changing right now. Now if I let the switch open, watch the needle again. So when I open the switch, the needle flipped again, flipped this time in the opposite direction over towards the right. So this is the same effect as the magnet being stuffed into or pulled out of the loop of wire. It's that whenever there's a changing magnetic field, I'm going to change it now, I get an induced EMF, an induced current. And I'm going to change it again now by switching the magnet off. I get another induced EMF, induced current. So those are two famous examples, illustrations of induction. And what they have in common, I mean, they look like very different experiments, but in a way, what they have in common is simply I'm changing a magnetic field and I'm seeing an induced current, seeing an induced EMF. And that's the effect of induction. Okay. Yeah, well, this is what I just said. In both of those, so I'm going to say it again. Both of those experiments, and all of Faraday's experiments on induction, he was one way or another way changing a magnetic field with a bar magnet, with an electromagnet, and observing an induced current or an induced EMF. And the big question then, that Faraday, this is Faraday again, that he's asking himself in this thought bubble, the big question he's asking himself, what is the law of nature that describes those different experiments? Now that sounds like a tough one, right? It's easy and straightforward now to see the effect that you get induced current, induced EMF when you change a magnetic field, when you increase, decrease a magnetic field. But what would be the law of nature, like the F equals ma of electromagnetic induction, that would describe this effect? So that was the next challenge. Okay. So to write down the law, the natural law, the law of nature that's describing induction, the phenomenon of induction, we've actually got to introduce the notion, concept of magnetic flux. Since we've already introduced the notion, concept of electric flux, I'm going to stand on those shoulders and rely on what we learn about electric flux as we introduce the magnetic flux. So this is a summary of what we learned about electric flux. Electrical fields create electrical flux. Electrical flux is is not something associated with a point, it's something associated with a surface. A way of visualizing electrical flux through a surface is just as the number of field lines, electrical field lines, that are passing through that surface. So here's a surface in beige here, or whatever this color is. Here's a field here in tangerine orange. And this field is passing through this surface. And if we wanted to visualize the size of the flux, the magnitude of the flux, we could just imagine counting the number of field lines that pass through the surface. If there was a lot of them, that would be a big flux. If there's a few of them, that would be a small flux. So that's how I visualize flux. To make that more mathematical, to make that more quantitative, let's think of the vector E, the electrical field vector, describing the field. And let's think of this vector A that describes the surface. It has a size that's the area of the surface. It has an orientation that's perpendicular to the surface. The electrical flux, we met this equation. You can write that electrical flux, phi subscript E for electric, as the product of the magnitude of the field, that's the E here, the area of the surface, that's the A here, times the cosine of an angle, and that angle theta is the angle between the direction of the field and the direction of the area vector. So that angle is really the relative orientation of the surface in the field, or the relative orientation of the field at the surface. So that's what theta is here. Well, in a classic example of recycling my slides, I've now turned this into a definition of the magnetic flux. So if we want to think about magnetic flux, again, magnetic flux, like electrical flux, is not about a point in space, like fields. It's about a surface. So you've got to think about a surface in a magnetic field here, like we thought about a surface in an electrical field. If you want to visualize the magnetic flux, well, let's picture this surface in beige here. Let's visualize these, this magnetic field here, indicated by the orange field lines. And the flux would be basically the number of field lines that are passing through that surface. So the more magnetic field lines that pass through the surface, the more magnetic flux. The less magnetic field lines that pass through the surface, the less magnetic flux. So that's how we picture the magnetic flux. And the equation for the magnetic flux, well, to write down the equation, we want to think about this vector here, B, is the magnetic field vector. It has a direction, it has a size or magnitude. We want to think about this vector A here. It represents the surface. It has a size or magnitude. It's the area of the surface. Has an orientation that's perpendicular to the surface. And then in terms of those two vectors, we can write down the magnetic flux. I'm calling it phi for flux, subscript B for field, B field. We can write it as the product of the strength of the field, B, area of the surface, A, times the cosine of this angle. And this angle is the angle between the two vectors here, between the magnetic field vector and the area vector. So it's the orientation of the field over the surface, or it's the orientation of the surface, in the field. And so, you know, what we learn about electric flux is exactly the same in terms of their definitions, their concept, their notion for magnetic fluxes. There's nothing especially new there. Just to give you a couple of examples, let's imagine I had a 1 square meter surface, and I just walked around the room putting the 1 square meter surface in different regions of magnetic field, and I put it at different orientations in the magnetic field. And I'm just going to calculate the, as I move the 1 square meter surface to different different regions of different field strengths, and move it orientated at different angles in the field. Let's just take a look at how the flux changes, how the flux through the surface changes. So in this example, it's a simple example, I've got a magnetic field that is strong over on the left-hand side here. It's 15 Teslas. The field lines are closely packed. It's weak over here on the right-hand side. It's just 5 Teslas. The field lines are loosely packed. And in the middle here is some intermediate field that's not as strong as the one on the left, that's stronger than the one on the right. If I put the surface perpendicular, the surface is perpendicular to the field, so the area vector is parallel to the field. If I put it in these 3 different fields and calculate the 3 different fluxes, I get a large flux through this surface. It's larger because the field is stronger. The surface area is the same. The orientation is the same. I get the smallest flux through this surface over here on the right-hand side. It's smaller because the field is smaller. It's 5 Teslas. The area was the same. The orientation was the same. And then in the center here, I get some intermediate flux. And that intermediate flux is because there's an intermediate strength magnetic field through this surface. I could see all that visually, pictorially, qualitatively, but just counting the field lines, right? If I counted the field lines through this surface on the left, there's 1, 2, 3, 4, 5, 6, 7, 8. So that's a large number of field lines, so that's a large flux. I've got 1, 2, 3, 4, 5 in the one in the center, so it's a smaller flux. And then I've just got 3 field lines, 1, 2, 3 here, through the surface on the right, so that's an even smaller flux. Anyway, that's just an example how flux varies with magnetic field. And that's going to be important to us. The other thing that flux varies with is the orientation of the surface in the magnetic field. So here's the 1 square meter surface again, orientated in the same strength magnetic field, 50 Teslas, but it's orientated at different angles. So in the case on the left-hand side, the vector B for the magnetic field and the vector A for the surface, they are parallel to one another. Theta is 0 here. In the center here, the vector A that's perpendicular to the surface and the field vector B, they're at right angles to one another. So the angle between them here is 90 degrees. Theta is 90 degrees here. And over on the far right here, we've angled the surface in the field such that the angle that's made between the vector A that represents the surface and the vector that represents the magnetic field, that angle theta is 30 degrees here. So for these 3 surfaces, well, the surfaces are the same areas. The fields are the same fields. It's just the orientations of the surfaces in the fields that are different. It's just the different orientations that we're exploring in this example. So if I calculate the flux in this case, I'd be calculating the magnetic field strength times the area times the cosine of 0 degrees. Cosine of 0 degrees is 1. It's as big as cosine theta gets. And so we get a big flux. In this case here, if I want to calculate the flux, it's the area of the surface times the strength of the field times the cosine of the angle between A and B. That's 90 degrees here. That's as small as cosine gets. So that's 0. So there's actually no flux through this surface. And then if I go over to the far right, again, if I want to calculate the magnetic flux through the surface, it's the product of the strength of the field times the area of the surface times the cosine of the angle between those 2 vectors, A and B. It's 30 degrees here. The cosine of 30 degrees is about 0.87, I think. And so it's not as big as 1 over here, but it's much bigger than 0 here. And so you get some intermediate flux here. So that's just to illustrate an example of how flux depends on the orientation of the surface in the field. Just like electric flux depended on the orientation of the surface in an electrical field. Again, you can visualize the flux, imagine the flux, by counting the field lines that cross the surface. So over here on the left, we've got 1, 2, 3, 4, 5, 6, 7, 8 field lines crossing this surface. That's the large flux. In the center here, look, there are a couple of field lines here, but they don't pass through the surface. This one skims across the top of the surface, this lower one skims below the bottom of the surface. There's no field lines passing through the surface, so this is zero flux. This surface here, it has some intermediate number of field lines passing through this surface. Let's count them up. There's 1, 2, 3, 4, 5, 6. So we get an intermediate flux. It's less than this flux, but it's much more than this flux. Okay. Here's just a little example problem. I don't know who thought of this problem, really, because it's kind of a little strange. But imagine, let's compare Greenland and Argentina. Let's just decide we want to compare Greenland and Argentina. And we want to compare, what do we want to compare? We don't want to compare their populations or their gross national product. No, we're going to compare the magnetic flux through Greenland and Argentina. Which one, Greenland or Argentina, has more magnetic flux? So Greenland's somewhere up here, and Argentina's somewhere down here. And interestingly, Argentina has a somewhat larger surface area, than Greenland. So think of Greenland, think of Argentina as two surfaces. One's a little bit bigger, Argentina. One's a little bit smaller, Greenland, that are immersed in a magnetic field. They're bathed in the Earth's magnetic field because the Earth's a magnet. And we just got to compare those fluxes. Well, it turns out that the flux through Greenland, although it has a smaller area, is larger. It turns out that the flux through Argentina, although it has a bit larger area, is smaller. The reason is the orientation of Greenland's surface in the magnetic field versus the orientation of Argentina's surface in the magnetic field of the Earth. So what makes Greenland's flux bigger is the orientation of Greenland's surface, and what makes Argentina's flux smaller is Argentina's orientation in the surface. You see, Greenland, the south, magnetic south pole is right up near Greenland. And so the field lines are pouring out through Greenland. They're basically sprouting out of the ground through Greenland. Argentina, on the other hand, wherever it is, somewhere here, the field lines in Argentina are much closer just to streaming across the surface of Argentina. Argentina is much further from the magnetic North Pole. Greenland is much closer to the magnetic South Pole. That means the field lines are coming vertically out through Greenland. The field lines are skimming across the surface through Argentina. And so Greenland, in the famous Greenland versus Argentina magnetic flux wars, then Greenland has won the war. It has much more magnetic flux, and Argentina has lost. Okay. Let's get on to, now we've introduced flux. That was a tool. We needed flux as a tool. If there wasn't the flux law, we wouldn't talk about flux. So we need it as a tool to write down a law of nature that's describing induction. That's the use of magnetic flux. So the law of nature that describes induction is called Faraday because he first discovered induction. Upstairs here is Faraday's law of nature describing induction. So it's this little equation here. In one sense, it's not a very long equation, so it's not scary. It's not like it's scary because it's long. It's more scary because of the things that are in it. I think the delta phi's and the delta t's make it a little bit scary. But let's see what it means. So in Faraday's law of induction, over here on the left-hand side, this is kind of the electrical world. And over here on the right-hand side, that's kind of the magnetic world. So firstly, the way I think of the law is it is that equal sign represent a bridge connection between electricity on the left, magnetism on the right. Because on the left, you've got epsilon's the electromotive force. That's an electrical potential that can drive a current. So that's an electrical quantity. Over on the right-hand side, you'll see a magnetic field. So that's obviously a magnetic quantity over on the right-hand side. And the equal sign is the bridge, is the link, is the connection between the two. The law says this thing here, what this means is the rate of change of magnetic flux. So remember, phi b we just introduced, it's magnetic flux. Delta phi b is the change in magnetic flux. It just means the change. And delta phi b over delta t means the rate at which it's changing. So it's kind of like velocity is delta x over delta t. It's the rate of change of your position with time, with elapsed time. This is the rate of change of flux, magnetic flux, with elapsed time. So it's like a delta v over delta t, but it's a delta phi over delta t. There's also a minus sign in here. This is actually very important. I'm not going to say much about it right now. We'll come to it a little later, and we'll give it even a special name. Inside Faraday's law is a minus sign, and that's called Lenz's law. So, you know, it's like stealing somebody else's equation. Faraday wrote down his law of induction, Faraday's law, and then Lenz comes along and names the minus sign in it Lenz's law. But anyway, that happened, and the minus sign is a very important feature of the law. Okay. So how does it work? So let's say that I move this magnet from the right towards the left such that the field inside the loop of wire here changes such that the flux, so this is the important thing where flux comes in, the magnetic flux through this loop changes. And we're going to imagine that the initial flux with the magnet far away was 0, so there will be no field lines passing through the loop. And then the final flux is 0.02 Webers, that's the units of flux, and that's represented by these 1, 2, 3, 4, 5, 6 field lines passing through the loop. So look, here, there was a change in magnetic flux through the loop when I brought up the magnet. It went from 0 flux through the loop to 0.02 Webers through the loop. And I'm saying I did that in half a second. Okay, I changed that flux in half a second. What's the induced EMF that could create or drive an induced current? The induced EMF is the change in magnetic flux that just occurred divided by the elapsed time for the flux to change. So all I got to do is divide the change in magnetic flux. We said the change was 0.02 Webers. By the elapsed time that was half a second, I get a voltage induced that's 40 millivolts, 0.04 volts. That's what we even see it here on the voltmeter. So that's Faraday's law, and it just described that effect very quantitatively. It sounded like to me when I first thought about Faraday's law, I said, how can you possibly write down an equation to describe sticking a magnet in a coil and things like that? Well, you can write down a very simple equation with this concept, this notion of magnetic flux. That's the key. Okay, now I'm going to pull the magnet out. I'm going to pull the magnet out, and that too, as I pull the magnet from, in the neighborhood of the loop of wire to far from the loop of wire, that's going to change the flux too. So when I pull the magnet out, the initial flux is at 0.02 Webers, and that's going to shrink away to 0. And let's say that I'm as fast or slow pulling the magnet out as I was pushing the magnet in. It took me half a second to pull it out. So to calculate the induced EMF in this loop of wire that would drive a current around the loop of wire, all I've got to do is divide the change in flux by the elapsed time. So the 0.02 Webers by the half a second. And again, I get, since the change in flux and the length of time were the same, I'm going to get the 40 millivolts, 0.04 volts again. And look, I even see it on the voltmeter. So that's the flux law. I got a quiz here. So right now, I do actually own a watch. Right now it's 10:11. I'll give you to 10:14. Incredibly generous of me. It's just the way I am, I guess. I'll give you a couple of minutes to think about this question, and then we'll talk about it. So this is a question in which we're, in one way or another, manipulating a loop of wire in a magnetic field. So one manipulation is to crush the loop of wire. Does that make an induced EMF? Other ways are to rotate it. Other ways, we try turning the field on and off. And then finally, we try moving it horizontally, left to right or right to left. And which one doesn't induce an EMF? Okay, let's answer this question. To induce an EMF through induction, you have to have a changing flux through your wire loop. So it's a matter of asking in each case, does the flux change through the wire loop? Supposing, and you could visualize that by thinking of the number of field lines that are passing through the wire loop. In the picture, there's about 1, 2, 3, 4, 5, 6, 7 field lines through the wire loop. If I crush the loop, I'm going to change that. There'll be none if I squeeze it down to nothing. So there will be an induced EMF there. If I rotate the loop, I could rotate it so that no field lines pass through the loop. There'll be an induced EMF there. If I turn the field on or off, right, that would obviously change the flux through the loop because I'm changing the field. The only one that doesn't change the flux through the loop is to slide the loop from left to right or right to left. If I do that, the same field lines are always passing through the loop. I'll induce no EMF. And so no EMF is induced when I move the coil in such a way that the magnetic flux through the coil does not change. Okay, I wanted to talk about Lenz's law. So Lenz's law is this minus sign in Faraday's law. And Lenz's law tells us about, informs us about the direction. When you get induction, you get an induced EMF. We often talk about that. You get an induced current. We often talk about that. And it tells us the direction of that induced current. It's really kind of a reminder of how you need to think about the direction of the induced current. You see, in this case I've sketched here, where we move the magnet into the loop of wire, the current could go this direction around the coil, right, come out on this right hand, can't get this to work now. This right hand lead here, it could come out on that and head back in through the left hand lead, or it could do vice versa, right? It could come out on the left hand lead and go back to the voltmeter on the right hand lead. Which one of those two? Which one of those two is given by Lenz's law? So the rule is that the induced current, so this is the current that's produced by the changing magnetic field. It's the one we give the name the induced current. The induced current flows in the direction, flows in the sense to create its own magnetic field. So that induced current is going to create its own magnetic field. I'm going to call that B induced. It's the induced magnetic field. So that induced magnetic field opposes whatever change is going on in the original magnetic field. So think about it in this case. The change in the original magnetic field is that there was no magnetic field at the location of the loop. Then suddenly there is a magnetic field towards the right-hand side, the left-hand side of the rope. So suddenly this field went wham, right? The induced current is going to try and create an induced field that opposes that change. The induced current is going to make an induced field that goes wham in the other direction, or bam, or whatever. It's going to go towards the right. So that's Lenz's law, that induced current is going to make a field in this direction. For a field in this direction, what sense must the current flow? Well, a right-hand rule from last class will tell us that. If we want a current that's towards the right, this is if we want a field, this is the induced field. If we want the induced field to be towards the right, my right-hand rule tells me that the current's going to come out of the screen upstairs and flow around and go back into the screen downstairs. So it's going to go in this direction. And so it's telling me the direction of the current in that loop of wire. It's this direction. What about when I pull the magnet away? So this is the same sketch, but now I've flipped the arrow. Now I'm moving the magnet out of the way rather than move it towards the loop of wire here. So what's happening from the point of view of the original magnetic field in this case? The original magnetic field was heading towards the left, so field lines pointing over towards the left of the room, and then they suddenly went away. So that magnetic field is gone. The induced current is going to make an induced magnetic field that opposes that change. So if the field towards the left went away, it's going to try and make a field towards the left. So it wants to make an induced field that goes towards the left. And so I'm going to point the thumb of my right hand in the direction of that induced field. So my thumb is the induced field towards the left. My fingers are going to curl in the direction of the current that I need to make that induced field. Now they curl in at the top, into the screen at the top, and come out of the screen at the bottom of the loop. And so that tells us the sense of the current. You notice that the induced field has reversed because the original field change has reversed, so the induced current is also reversed. So everybody's reversing in this little game. And that's Lenz's law. Let me show you another example of Lenz's law on this overhead here. So this is an example of Lenz's law where we don't have moving parts, right? We're not moving a magnet around. We're not sticking it in a coil or pulling it out of a coil. Everything's stationary, except I've got an electromagnet that I can switch on and switch off. So here are 3 sketches of the arrangement that I built. It's really this arrangement here, one coil in the neighborhood of another coil. One coil is connected to a power supply that I can energize. The other coil gets an induced EMF, gets an induced current. So in this picture, which I've just copied 3 times as I do 3 different things, in this picture, here is the electromagnet that's going to create the magnetic field when I close the switch. And then here is the coil that's going to experience an induced EMF, experience an induced current. And what we're going to do is we're going to start over here. This is, the switch is open. The electromagnet is off. We're going to energize the electromagnet, and we'll see induction at that moment. And then later on, we're going to de-energize the magnet, and we'll see induction at that moment too. And our question again is, when I get induction, when I switch on the magnet, and when I get induction, when I switch off the magnet, what is the direction of the currents that flow in the coil that experiences the induction? What is the direction of the current flowing in the coil here as it experiences induction? The current could come out at the top of the screen and go back in at the bottom screen. That's one sense, one direction. The current could come out at the bottom and go back in at the top. That's the other sense, the other direction. So which of those 2 possibilities? It's Lenz's law that picks between those 2. So let's start with the one in the center here. This is where we've just switched on a field. And again, if you look at this situation, I imagine I'm the coil. So I'm the coil, just sitting here, and wham, suddenly there's a magnetic field. There's a magnetic field that's heading towards the left-hand side of the room. You can see those green magnetic field lines of the electromagnet heading through the coil towards the left-hand side of the room. Lenz's law tells me that the induced current that I'm now going to experience is going to be a current that flows in a direction that opposes that change. It creates a magnetic field that opposes that change. I don't like change. And if I'm a coil, I also don't like change. So I'm going to try and make a magnetic field that heads towards the right to oppose the change, the new field that went towards the left. So the induced field, B induced, is going to be towards the right. I've indicated that on the sketch. And so the question is, what current direction do I need to produce to make that induced field towards the right? Well, it's the right-hand rule that will tell me that. I'm going to point my thumb towards the right. My fingers are going to curl in the direction of the current. Look, they're coming out of the screen at the top, and they're going back into the screen at the bottom. And so that's the sense, this sense, out of the top, in at the bottom, that creates that, that's the sense of the current. And we got that with Lenz's law. What about when we turn the electromagnet off? When we turn the magnet off, this field, this green field, the field of the magnet, goes away. And so when it goes away, that's also a change in flux. There's going to be an induced current, induced EMF. What is the direction of the induced current here? So let's use the same arguments. So again, imagine I'm the coil. I'm the coil, and I'm bathed in this magnetic field. Here it is, and then bam, it's gone away. So I'm a coil, I don't like change. I'm going to induce a current that tries to oppose that change. I'm going to induce a current that produces an induced magnetic field that replaces that original magnetic field. So I'm going to make a magnetic field that's heading towards the left now. what direction of current am I flowing? Well, I can use the right-hand rule for a current loop to figure that out. I'm going to point my thumb in the direction of the induced magnetic field that I need. It's towards the left to replace the original magnetic field that was also towards the left. My fingers now they're curling in towards the screen upstairs and curling out of the screen downstairs. So the current that's producing the magnetic field, induced magnetic field, when I turn the coil off, is that current is flowing in on the coil, on the loop at the top, and flowing out of the screen at the bottom. So that's Lenz's law again. Okay. Let's look at some illustrations, some examples of Faraday's law. This includes some quantitative calculations involving Lenz's law. So let's try and do that. See if I can. Okay. So I mean, I copied this from the textbook. I don't know what this thing is, but a transcranial magnetic simulation device. So creates a magnetic field. I've lost the 1.5 Tesla field in 12 milliseconds. So this field appears in a time interval of 12 milliseconds over a 1.6 millimeter radius circle, so a tiny circle of my brain. Okay, that's going to induce a current in my brain. It's going to induce a EMF in my brain, and it's going to, I don't know, it's going to get my brain working again. It's going to fix my brain. Hopefully, this isn't drawn to scale. But here's my brain, and here's the loop in which we're inducing this EMF. And we're inducing it by changing the magnetic field by 1.5 Teslas. And so our job here is to determine this induced EMF. Let me write it out on the... on the device that I can't remember the name of. Let's solve it here. So I started the problem. I got a region of my brain in which the magnetic field has changed by 1.5 Teslas, and that region of my brain involves a circular loop that's radius is 1.6 millimeters. And so I want to calculate the induced EMF. To calculate the induced EMF, I'm going to have to know the flux change, and I'm going to have to know the time interval. Now, the time interval over which the flux changed, we were just told that. That was 0.012 seconds. So that's simple enough. To calculate the flux change, I've got to calculate that from the magnetic field change using the definition of flux and the area of the loop. So the first thing I'm going to need is really the area of the loop. So the radius of the loop is 1.6 millimeters. The area of that loop is going to be pi r squared, that famous bit of geometry. So I've got pi, 3.14, times the radius squared, so is 0.0016 meters squared. And that area I got was 8 times 10 to the minus 6, tiny in square meters, because it's only millimeter size. It's 10 to the minus 8 square, 8 times 10 to the minus 6 square meters. Okay, now we need the flux, the change in flux. Well, the change in flux is, the loop is is the field lines are passing through the loop. The area vector of the loop is parallel to the field lines. So the change in flux in that case is just the change in field times the area of the loop, times the cosine of 0 degrees, but I won't write that down. So we've got to multiply 1.5 Tesla by 8 times 10 to the minus 6 square meters. That's going to give me 1.2 times 10 to the minus 5 Webers. Webers are the units we use for flux. Now I can calculate the induced EMF. And I'm just going to worry in this problem about the size of it. We were only asked about the size of it. The size of the induced EMF is the size of the change in flux, delta phi, divided by the elapsed time, delta t. We know both these numbers, so we've got 1.2 times 10 to the minus 5 Webers change in flux. We've got an elapsed time that's 0.012 seconds. And so if you divide one by the other, you see you've got, it's actually 12 times 10 to the minus 3 dividing 12 10 to the minus 6. So it's actually just 10 to the minus 3. We've got 1 times 10 to the minus 3 volts. 1 millivolt. That's the induced EMF. Anyway, that's an example of calculating with Faraday's law that describes induction and induced EMF. And this is I can't remember the name of it either. Transcranial magnetic something device, right? This is a real thing that is used to create little voltages, little voltage sparks in your brain for some reason I don't know. But anyway, it's a real device. That doesn't change that. Okay. Another question about law of induction. This one's about, what's this one about? This is about Lenz's law. So in this particular problem, we've got a current carrying wire. The current is flowing vertically upwards on this wire in the center of the screen. And then we've got 3 loops, 3 coils, 3 rectangular coils, A, B, and C, either on the left or the right of the wire. And they are being moved with respect to the wire. So the current carrying wire is creating a surrounding magnetic field. We met that magnetic field in last class. That magnetic field, if you think about it, is loops of field lines that is strong if you're near the wire and weak if you're far from the wire. And they revolve around the wire. They circle around the wire. They're centered on the wire. So you have to imagine that in all this region here is bathed in magnetic field, bathed in magnetic field lines. And we're moving this loop A, we're moving this loop B, we're moving this loop C through that magnetic field. And the question is, what, if any, induced currents are produced in the loops A, B, and C? So let's see if we can figure that one out. And for this one, maybe I'll stay on the slide. So this is how I figured it out. So the first thing I did, this is kind of busy, but what did I do here? The first thing I did, I said that current carrying wire is producing a magnetic field. Why don't I just kind of ease my way into the problem by drawing that magnetic field? That'll calm me down, and it'll give me a sort of landscape of field on which to figure out the directions of the induced current. So the green dots and crosses are my sketch of the magnetic field. What I'm trying to sketch is, look, the right-hand rule for the current carrying wire, if I point my thumb in the direction of the current, it says that the field lines come out of the screen on the left of the wire, head back into the screen on the right-hand side of the wire. and they circle around the wire. So over here on the left-hand side, right, you see the field lines. The dots means the fields are coming out. Field lines are coming out. The crosses over here on the right-hand side, that means the field's going in towards the screen. The field lines are curling into the screen here. So that's the first thing. Out on the left, in on the right. Second thing, the field of a current-carrying wire falls off with distance from the current-carrying wire. It falls off as the inverse of the distance from the current-carrying wire. So if you double the distance, you're going to have half the field, and so on and so forth. So that means that near the wire, the field is strong. Far from the wire, the field is weak. So I try to draw these dots closer, because they're nearer the wire, than this pair of dots. They're further from the wire. This is indicating the field is stronger here, and it's weaker over here. Likewise, these crosses, the two closest to the wire, are closer than the two crosses further from the wire. That's showing that the field is stronger here than it is over here. And so that's the landscape of magnetic field that surrounds the wire. Strong near the wire, coming out of the screen on the left, into the screen on the right. That's what we need to know. Now we can imagine the loops, A, B, and C, I think, moving through that field. And we can ask the question, what are the induced EMFs based on Faraday's law, based on we need a changing flux to make an induced EMF, and based on Lindsays' law, which tells us the direction of the current, based on the changing field. The first one, let's do this one here. What's the flux change through that loop? That loop is just being pushed or pulled vertically upwards in the magnetic field of the current-carrying wire. As it flows upwards, that loop, the field's always the same. It's not getting closer to the wire. It's not getting further from the wire. The field's always the same through the loop. So the flux is always the same through the loop. So it's easy to answer the loop that's just moving vertically upwards. There's no change in fields. There's no change in flux. So there's no induced current. There's no induced EMF. No current in this guy here at all. What about this guy? This guy, this was B. B, she, is moving towards the left-hand side. So B is it starts out in a region where there's a lot of field lines coming out of the screen through it, and it moves over here to a region where there are less field lines passing through it. So what is, if I'm loop B, what am I seeing? What am I experiencing? I'm experiencing through me less and less field lines going through my loop. And so I am experiencing a field that was out of the screen through me, and then it's just going away. And so I'm going to try and replace it. My induced current is going to make an induced field that tries to replace it. So my induced field is out of the screen, because I'm replacing one that was out of the screen. If I want a field that's out of the screen, if I'm a current loop, well, I can use the right-hand rule. I can point my thumb in the direction of the induced field that I'm trying to make. It's out of the screen to replace the original one. My fingers curl in the direction of the right hand, curl in the direction of the current, so they're going to head up the loop on the right-hand side, towards the left over the top, and then back downwards on the left-hand side. And so that's the direction of the current that I showed here. So this induced current is counterclockwise, is making an induced field that is out of the screen, and it's replacing the loss of the original field that was out of the screen. Let's try this guy over here on the, this is the right-hand side. So now I'm going to play the role of that coil. So here I am. I'm bathed in a large magnetic field, lots of field lines that are passing through me towards the screen, away from you. I'm going to start moving towards the right, and those field lines are just vanishing away. as I get further and further from the current carrying wire that makes the field. So if I'm that current loop, what do I see? I see a field that was through me towards the screen, and it's disappearing. I'm going to try and replace that field. I want to make a field, my induced field, that goes towards the screen. So that's Lenz's law. To make an induced field that's towards the screen, I can use the right-hand rule to figure out what direction the current's going to flow. I'll point my thumb in the direction that I want the induced field to be, towards the screen. And my fingers will naturally curl in the direction of the current. So they're curling on the left-hand side of the loop, they're coming up. Current's then going across towards the right, across the top of the loop, and then it's going downwards over the right-hand side of the loop. And so that's the direction here. This is a clockwise direction, and that's what I've indicated on the screen here. So again, this is example of how we can use Lenz's law to figure out the direction of the induced currents in a circuit based on the fact that they create induced magnetic fields that are opposing the change. And so that's an example of Lenz's law. Okay, look, I've only got a couple of minutes here. I'll post this one online. Let me just stress what we've done today. Up until this point, electricity and magnetism were separate worlds, separate landscapes, separate forces. Today, we've begun the momentous and important task that will lead to modern technology of joining together electricity and magnetism. And the first step is induction, electromagnetic induction. We looked at the law of electromagnetic induction. It's Faraday's law, and we looked at a component of it, which is Lenz's law. And we looked at some illustrations and examples.